As Aldo said, today I'm going to talk about large-scale optimization for machine learning and data science. So I guess you guys will agree with me that over the last decade we have witnessed the success of machine learning and data science. And I think it's mostly due to the advances in computational power, representation, and algorithms. And when we talk about advances in algorithms, we mainly talk about optimization algorithms, as several problems that we face in machine learning and data science can be formulated as an optimization program. And my work has been on developing optimization algorithms for modern machine learning and data science problems that appear in different application domains such as recommender systems, Internet of Things, and autonomous systems. But before talking about my research, let me just give you an overview of, I think, the challenges that we face in designing algorithms for data science. The first challenge is large-scale data sets. So in many machine learning applications, such as ad clicking or recommender systems, you are given a massive number of samples, and you want to train your model using the elements of this training set. But the challenge is if you want to use traditional algorithms that are developed for classical optimization problems, their computation complexity is going to scale poorly with the size of the training set. So we need to come up with an algorithm that can handle large-scale data set, and they are basically computationally efficient. The second challenge is non-convexity. Also, in several application domains, such as deep learning or coverage problem, which is an instance of submodular maximization, we face an optimization program where the loss function is non-convex. So indeed, solving a non-convex problem is more challenging than the convex optimization. And if you just try to use traditional optimization algorithms that are originally designed for convex optimization for solving non-convex problem, they either fail or perform poorly. So we need to come up with algorithms that are originally designed for non-convex optimization. The third challenge is distributed systems. In several application domains, such as Internet of Things, transportation, wireless communication, we face basically a physical systems in which a group of agents are gathering data and information, and they want to come up with an optimal decision in a distributed way without any global coordination. And this is a very challenging task if you want to come up with an algorithm for such settings, because you want to come up with an algorithm that can be implemented in a distributed manner without global coordination. And last but not least, we are facing time-varying models. So in several applications, such as robotics, autonomous systems, or power systems, we face a problem that the dynamic of the problem changes over time. So for example, if your drones enter a new room that has a different temperature, or there's an obstacle in the room, the dynamic of problem is changing. Or if you have a power systems, if you have a failure in the networks, then the constraint sets that you have to satisfy might change. So we need to come up with an algorithm that they adjust themselves based on the changes in the dynamic of the problem. So these are the 4 challenges that we face in designing optimization algorithms, or in general algorithms for solving data science problem. And over the last 6-7 years, I've contributed in all these 4 topics. And you can see an overview of my publications here. But however, as we have limited time, I'm not going to focus on all these topics. And I'm just going to focus on one of these corners, which is about large-scale learning. And in particular, in the first half of the talk, I'm going to talk about the stochastic methods for solving large-scale learning problems. And in particular, I'm going to focus on the stochastic quasi-Newton methods. I'm going to talk about all these words in the first half of the talk. And in the second half of the talk, I'm going to use tools from statistical learning and optimization theory to come up with computationally efficient algorithms for solving large-scale learning problems. OK, before introducing large-scale optimization formulation, let me just first motivate the problem with a simple example. Think of this ad clicking problem where you, as a user, you search for a product, let's say Inter Milan jersey, and you search Inter Milan jersey in the tab of Google Chrome. And then the search engine, which is the Google here, wants to come up with an ad that has the highest probability to be clicked by you as a user. So the problem is the user search for something, you want to show an ad with high probability. This problem can be formulated as a classification problem where your feature vectors, xi's, contain information about the web search, user information, and the ad that has been shown to the user. And your label is either, of course, 1 or -1, depending on the fact that the user has clicked on the ad or not, right? And W would be a predictor which says that given xi, what would be the label yi if I have access to xi, right? And W star is the best predictor over all the elements that you have access to in the table. This problem can be formulated as this optimization program where W star, which is the best predictor, is the best predictor over all the elements of the training set given a loss function, where the loss function measures how well W predicts the level of Xi, which is Yi. This is a very well-known problem, and what's interesting about this problem is that the objective function can be written as the sum of n functions, where each individual function corresponds to a sample in the training set. We also use the phrase empirical risk minimization for this specific optimization problem. And the main challenge that we face in large-scale empirical risk minimization or large-scale optimization is that the number of samples that you have in the training set is massive. For example, in this ad-clicking problem that I just introduced, typically the size of training set is ordered 10 to the 8 or more. Or in another very popular machine learning application, which is called recommender systems, the size of training set is ordered 10 million or above. So, okay, the question is, how would we solve this large-scale learning problem? So, I'm pretty sure you all know a stochastic gradient method, which is perhaps the most popular algorithm for solving this class of problems. The idea is very simple. I use a subset of samples, evaluate the gradient corresponding to those samples, and try to update my model using this simple update. Here is the average of gradients, and this is the step size, and you update your model using this simple update. So what's nice about this algorithm, it's computationally cheap because you just use a subset of samples in the training set. However, the convergence performance of this algorithm is not very fast. It is actually very slow. And there are two reasons that this algorithm is very slow. The first reason is we are using noisy gradients. When you're using noisy gradients, the direction that you're following is not the exact gradient, so you're jumping around that. But on average, you're going to reach the optimal solution. But since it's noisy, you have to kill the noise of approximation using a diminishing step size, which leads to exact convergence. But over the last 5-6 years, people have come up with smart ideas to reduce the noise of stochastic gradient approximation, either by using memory or computing the gradient of the full objective function once in a while. And they could achieve linear rate, which matches the linear convergence rate of gradient method. And that's very nice. They're computationally cheap, and they achieve linear rate. But the second issue that the stochastic gradient method suffers from is poor curvature approximation. And this issue is inherited from gradient-based methods because they just use first-order information to update the model. They don't use any information about the curvature of the function. And because of that, when the problem is ill-conditioned, then the convergence rate is going to be slow. So people, including myself, they have used the idea of a stochastic quasi-Newton methods to resolve this issue, to come up with better curvature approximation for the update of variable, which leads to better performance in ill-conditioned problems. I'm going to talk about all these 2 points in detail in this talk, in the first half of the talk. But in particular, I'm going to talk about an algorithm called IQN, which basically resolves both of these 2 issues. And it's computationally cheap, and at the same time, it achieves a super linear convergence rate, which is better than the linear rate that we have seen for the first group of algorithms. Okay? So before talking about IQN, let me just focus on the poor curvature approximation issue of first-order methods. So here, this is a toy example, a quadratic problem, and I'm showing the convergence path of gradient descent, which is the black one, a stochastic gradient descent, and 2 of these variance-reduced algorithms that I presented here. So as you can see, gradient descent has a linear rate. When you have a logarithmic scale, it goes on like a line, so it's linear. But because of the computation complexity, it's very slow. A stochastic gradient has a sublinear rate, and it's faster, but faster than gradient. However, it's slower than these algorithms that are computationally cheap and also have a linear convergence rate. So it seems like everything is good here. But I make a simple change. I change the objective function in a way that the condition number of problem is going to be multiplied by 10. And here is going to be the performance of these algorithms. As you can see, their performance worsens significantly once you increase the condition number of the problem. And you might ask why we see this basically observation. The reason is they suffer from poor curvature approximation, and this is something that is inherited from gradient method. It's not because of a stochastic gradient, it's just because you are using first-order methods. Originally, first-order methods are designed for problems that have good condition number, and the function level sets are close to circle. So for example, here, if you look at the direction of gradient, it's towards this way. And if you follow negative gradient, you move towards the optimal solution. But if the level sets are not in a nice shape, and you have a large condition number, when I say condition number, it's basically the ratio between this diameter and this one. If it's large and your problem is ill-conditioned, then by following the direction of gradient, you're not moving towards the solution. You're slowly approach the solution in a zigzag move way, but your direction is not as good as the one that you have when you have good level sets, basically. So you might ask, why do I care about ill-conditioned problem? Because in many high-dimensional problems, including the click-through rate prediction problem that I just explained to you, the dimension of problem is large, and the condition number as a result of that is also very large. For example, in this example, the condition number is order 10 to the 7. And if you use these first-order methods, you're going to see performance like this. So we need to use some sort of curvature approximation to come up with faster algorithms. And in particular, I'm going to talk about the stochastic quasi-Newton methods. But before doing that, let me just give you a very quick overview of quasi-Newton algorithms in a deterministic case when you have actually access to the gradients. So the idea is very simple. The only difference is you pre-multiply the gradient with a positive definite matrix that you hope is going to be a good approximation for the Hessian of objective function. So if I simply replace this by the Hessian of the objective function, I recover the update of Newton's method. But I don't want to compute the Hessian or Hessian inverse because that's costly. So I want to come up with a very computationally efficient way to approximate this matrix only using first-order informations or gradients. And there have been several algorithms in the 60s trying to tackle this problem. There are different variants of quasi-Newton methods, including Broyden method, DFP, and BFGS. But today I'm going to focus on BFGS, which is the most successful quasi-Newton algorithm. So the idea is simple. To understand the update of BFGS, I just need to define two vectors. One is variable variation, which is the difference between two consecutive variables. The other one is gradient variation, which is the difference between two consecutive gradients. So you want to come up with a matrix that satisfies secant condition, where the secant condition ensures that your Hessian approximation times variable variation is close to gradient variation. You might ask why this equality makes sense. Like we have seen in calculus 1, the second derivative is almost the difference in first derivative divided by variable derivation, right? So this is just a vector form of approximating second-order information. So you want to come up with a matrix that satisfies this inequality. However, there is no unique solution for that. So what we do, we say that, OK, let's look for the matrix that satisfies this function and also is the closest matrix to the previous Hessian approximation. Because you know that the Hessian is not going to change significantly if you move a little bit. So OK, if that's the case, if you enforce these two conditions, you get this nice expression for the update of BFGS, which is a rank 2 update, and it can be implemented very easily. And what's nice about this algorithm, it has a superlinear convergence rate, which is close enough to the convergence rate of Newton and better than linear convergence of gradient-based methods. But however, I'm using gradients here. So in 2007, Sherdorf and his collaborators said that why not just replace all the gradients with the stochastic gradients? The easiest thing to do, right? And they had this paper without any theory. They showed that if you replace all the gradients with the stochastic gradients, you see these two algorithms. This is a stochastic BFGS, and this is a stochastic limited variant of BFGS, which is just basically a smarter way of implementing BFGS using less memory. But however, we look at this problem and realize that sometimes the stochastic BFGS method or OBFGS diverges. And that was one of the reasons that they couldn't come up with any theory, because I'm pretty sure that if you run this algorithm, you would see sometimes there is a spike in the performance of the algorithm. And the reason is, since you are using noisy gradients, there is a chance that your Hessian approximation can become arbitrarily close to become singular. And for that reason, the inverse could be unbounded, and you would see some spikes like this in the convergence path of a stochastic BFGS. So in my first work in this direction, we said that we came up with regularized stochastic BFGS, where we ensure that we are still satisfying secant condition, which is the fundamental property. We change the proximity condition in a way that we ensure that the matrix is not going to be singular, and we also use a stochastic gradient. And we could show that this algorithm is provably convergent and has better performance in ill-conditioned problems, as you can see. And this was the first provably convergent stochastic quasi-Newton method that we developed in 2014. And in 2015, in a follow-up work, we showed that the limited memory version of this actually does not suffer from this issue, and it also provably converges to the optimal solution almost surely, and it has a sublinear rate of 1 over t. So, definitely.
So when you talk about superlinear convergence or radical convergence or linear convergence, you're talking about convergence rate in iteration number.
Correct.
Right? So whereas in the stochastic case, the information field is bound. If you count the total amount of work that is order 1 over square root of work, you can never go faster than that.
Yes.
The information field is bound.
Yes.
So can you say more about this? Because I wonder if measuring convergence rate in terms of iteration number is the wrong metric.
Well, that's a fair point. If you look at the problem that is defined as a stochastic optimization, this is not a stochastic optimization. This is finite sum optimization, right? So, and I don't see how you, like, there is no information theoretic bound, then you have a finite sum problem. A finite sum problem is basically a deterministic problem. So you can get a linear rate or superlinear rate for that, even assuming that you can compute the exact gradients or Hessian, right? If you are solving exactly the stochastic optimization problem, your point is valid, actually.
So that device is not so great algorithm. I'm just giving you just to understand all of this. Let's suppose somebody says, go through and evaluate the gradient fully.
Yes.
At every step, you're going to evaluate the complete gradient. Now, implement BFGS on it.
Yes.
Right? That's a deterministic problem.
Correct.
So unless you take into account the complexity associated with capital N.
Indeed, if you do that, then the n term is going to appear somewhere, right?
Yes.
But if you do incremental method, like it's not going to appear. Like basically, you can show that dependency on n is going to be better. I'm not saying that it's going to be, like the point is each update, you're not going to use all the elements in the training set to update the model, right? You're going to use a subset of them, as I'm going to show in the next slide. So by using memory of order n, you can actually get the performance that you would get by using all the information, but without doing that with just one update per iteration, you can get the same performance if you use some sort of memory or variance-reduced algorithm. But if you just do naive stochastic approximation like this, then you don't get better than 1 over t, right? And 1 over t is actually the lower bound for a stochastic system when you have a strongly convex function. And that's definitely the lower bound. I don't know about...
No, it is the information theoretic bound. It is the bound. You cannot do, it is not a bound,
So-
it is the bound.
So you're telling me that the stochastic optimization, you cannot get a 1 over t rate in a strongly convex case?
No, you can do no better than 1 over t, and you can do 1 over t.
Exactly, that's what I agree. You cannot do better than 1 over t, I agree with you. But that's for a stochastic setting. But it's finite sum if the structure is different. You're not talking about like a distribution that you're sampling from that. We approximate that with a finite sum problem. And once you reach that regime, it's a different game. But if you want to solve the original stochastic optimization problem, you're 100% right.
Let me proceed, and hopefully I'll see. I don't know if the final results will involve a capital N in your complexity, but please proceed.
Sure, definitely. So basically what's nice about this algorithm, they have good performance in ill-conditioned problems, but as they have a sublinear rate, they're going to eventually be worse than linearly convergent first-order methods. Because the issue is you have a sublinear rate and they have a linear convergence rate. And if you want to have very accurate solution, then your performance is going to be worse than first-order methods. And the reason is we are still using noisy gradient, and we need to come up with some variance-reduced ideas to get at the same time better curvature approximation and a better convergence path. And this is what we proposed recently in our last work in this direction, which is IQN, this blue line, as you can see. It uses the idea of quasi-Newton update to come up with better curvature approximation. It uses memory to reduce the noise of gradient and Hessian approximation, and it also uses a corrected Taylor's expansion to approximate the functions. I'm going to talk about all these points in the next slide. So here, to reduce the noise of gradient and Hessian approximation, we need to use memory. So if you have n functions, you need a memory of order n to keep track of the gradients corresponding to each function and the Hessian approximation corresponding to each function as well, and the variables. So the idea is you update your model using all the information that you have in the memory, but once you update your model or you iterate, you just evaluate the gradient and the Hessian approximation for one of the functions. So you pick one function, you evaluate the gradient for that at the new point, and for that specific function, you also update the Hessian approximation that you have, right? And once you do that, you just replace all the old variables with the new ones. But if you notice that I just evaluated one gradient per iteration independent of n, right? But I'm aggregating the information of all the functions to update my model, right? This is a very standard technique for reducing the variance of stochastic gradients, and we are extending that basically to the second order methods. So there are two questions that I haven't answered yet. The first one is, how do I update this Hessian approximation matrix? And the other one is, how do I update the iterate? So updating the Hessian approximation is pretty simple. I have the old gradient corresponding to that function. I have the new gradient. I have the old variable and the new variable and the previous Hessian approximation. So basically, I can just follow the update of BFGS and define the variable and gradient variations to update my Hessian approximation matrix, right? The challenge is how should I update the variable using the information that I have access to? The natural thing to do is you look at the average of Hessian approximation, compute the inverse, and multiply that by the average of gradients. This seems like a natural thing to do. However, if you do that, you don't get a superlinear convergence rate in terms of number of iterates. And the challenge is, if you look at this update, basically it's a solution of this Taylor's expansion, this basically quadratic approximation for the function. So here, if this update is the solution of approximating your global objective function using this Taylor's expansion, where the gradient for function I is evaluated at the current variable zit, but the Taylor's expansion is centered at wt, which is something different from the zit, which is the variable corresponding to function I. And for that reason, you see an inconsistency in the Taylor's expansion. Once you replace wt by zit, which is the variable corresponding to function I, you have a consistent quadratic approximation. And once you solve this quadratic program, you get this nice update, which is a bit different from the update of BFGS, but it makes sense because there is a connection with this Taylor's expansion. And what's interesting about this algorithm is that for the implementation of this algorithm, you don't actually need to compute the inverse of this matrix, because the update of this matrix is a rank 2 update, and you can apply matrix inversion lemma twice to compute it at a complexity of order p squared, where p is the dimension of the W. Right? And it's a true incremental method because we just update the information of one function at each iteration. Okay, so then let's look at the performance of this algorithm. Here is the bound that we have, and I hope this addresses your question. It shows that the error at the current iterate is bounded by a sequence where this sequence converges to optimal solution superlinearly, and this is the definition of superlinear. So this means that the sequence of iterates generated by IQN, it converges superlinear to the optimal solution. And this is the first incremental quasi-Newton method that has a superlinear convergence rate, which closes the gap between deterministic and incremental quasi-Newton methods. Okay? So now let me just wrap up the first half of the talk by presenting some numerical experiments for IQN and all these first-order variance-reduced algorithms. In the left plot, I'm looking at the problem that the condition number is 100. In the right plot, I'm looking at the problem that the condition number is 10 to the 4. And as you can see, IQN outperforms these linearly convergent first-order methods. But once I increase the condition number of the problem, basically the gap between these two classes of algorithms is even more significant, as we expected. Okay, so in the first half of the talk, I talk about the stochastic methods when you separate samples over time and you just use a subset of them at each iteration to update the model. And in the second half of the talk, I'm going to talk about adaptive sample size methods, which uses tools from a statistical learning theory to come up with more computationally efficient algorithm for solving larger scale learning problems. And I'm going to focus on both convex and non-convex settings. Okay, so far I talked about empirical risk minimization. And in the empirical risk minimization, as I said, you're looking for a solution or predictor that performs the best over all the elements of training set that you have access to, right? So why do we call it empirical risk minimization? Because we don't have, the data is generated by a distribution. We don't have access to that underlying distribution that generates data, but we can sample from that distribution and use the empirical distribution as a proxy for the original true distribution that we don't have access to. So actually, the goal is to solve this expected minimization, where you want to come up with a classifier that performs best with respect to the probability distribution that generates data. Since we don't have access to that, we just use an empirical distribution to approximate that. So this simple observation means that there is no need to solve the ERM problem beyond the statistical accuracy, which is the gap between these two functions. You don't need to solve this exactly. And the question is, how accurate should I solve this problem, which has something meaningful, which has a meaningful outcome? And the solution is given by a statistical learning theory, which shows that the gap between empirical risk and its expected loss, it's actually bounded by a constant order Vn, where Vn is order 1 over square root of n, where n is the number of samples that we have access to. Indeed, if you have more samples, the gap between these two functions is smaller. And for some specific class of functions, it can be shown that this gap is order 1 over n, which is better. So this simple observation means that there is no need to solve the empirical risk minimization problem beyond the statistical accuracy, which is Vn, right? And also, if my problem is convex, I can add a regularization term of order Vn to the objective function. It's going to move this solution, but it's not going to move the solution more than order Vn. So it means that the solution of this regularized problem is going to be still in a ball of order Vn away from the solution of expected risk minimization. Okay, so then the goal would be to solve this regularized empirical risk minimization problem within the statistical accuracy, which is Vn, right? Finding a point that the error for that is order Vn. That's the goal, yes?
So, very first statement on the slide, what are the regularity conditions under which?
Yeah, that's a very good point. For example, if you have a strong convexity or for logistic regression, it has been shown that you can improve that from 1 over square root of n to 1 over n. That's
I'm asking to say in the previous point, that you're looking at the suit difference,
yes.
the population expectation
Yes.
minus your empirical
Correct.
approximation, and saying that that is uniformly bounded by some Vn with high probability.
Yes, but there is some constants I'm hiding.
So under what conditions on the objectives does that happen?
Yeah, exactly. So there's going to be a VC constant there that I'm hiding there. And depending on the classes of the functions that you are using, the constant that appear here is going to be different. But I'm putting everything inside this O factor, and I just show the dependency on over 1 over square root of n. But basically what you're, depending on the classes of functions that you're using, and the max value that you can see, the constant that you have here might change, which is the VC, basically, dimension of the problem. Okay, so I talked about the property of empirical risk minimization and saying that there is no need to solve this problem exactly. But there is another property that we can use that we didn't use in the first half of the talk when we look at this problem as a finite sum minimization problem. These samples are coming from a distribution. The distribution is unknown, but they're coming from a distribution. So that means that if I solve the problem, let's say for 1,000 samples, and if I add 10 more samples to that, the optimal solution is not going to change significantly because all these samples are coming from the same distribution. So that means that if I solve the problem for a small number of samples, and then I add more samples to that, the solution is not going to change significantly, and I can come up with this idea of adaptive sample size, which is basically saying that let's solve the problem for a small number of samples, and then increase the size of training set by a geometric factor, let's say alpha, which is larger than 1, and use the solution as for the smaller problem as a warm start for the next problem with more samples. But it's important to ensure that the larger set contains the smaller set. This is something that we formalize in our paper. And what's interesting is that, of course, solving the problem with a smaller number of samples is easier because the computation complexity of solving that is smaller. You have less samples. It can be shown that the condition number is also smaller and better, and the accuracy that you need is smaller, so that means that it's easier to solve the smaller problem. Okay, so then the question is, if I solve one of the problems, how should I update my iterate to solve the next problem? So we propose this algorithm called Add and Newton, which is a combination of adaptive sample size methods and Newton's algorithm. So the idea is very simple. You solve the problem for the first problem up to its statistical accuracy, and after that, you just increase the size of training set and perform a single iteration of Newton's method. If the size of training sets for the smaller problem and the larger problem are close to each other, with a single iteration of Newton's method, you can solve the larger problem up to the statistical accuracy. And you might ask why it works. The reason is I can use this cartoon to actually explain the idea. So if you have solved the first problem up to the statistical accuracy, and this is the optimal solution, you're somewhere in this neighborhood. And if the size of these two problems are close to each other, the solution that you already have is in the quadratic convergence neighborhood of Newton's method for the next problem. So that means that if I perform a Newton's update, I'm going to quadratically converge for the next problem, and I'm going to reach a point that is going to be in the statistical accuracy of the next problem. Yes?
Can you emphasize what it means to solve within statistical accuracy? Are you saying within the
So you reach a point, yeah. For each of the sub-problems, you want to make sure that you reach a point, if it is replace n by m, Rm of W minus Rm of Wm star is order Vm.
And can you say more about why it should not be square root of Vn, for example, standard error?
A square root of Vn, or Vn is order 1 over square root of n.
Yeah, it's not a variance.
No, if Vn is this. I said it's 1 over square root of n. Yes. Up to statistical accuracy of the square root of n.
Vn is the square root of the variance. It's like a standard error.
Yes, exactly.
And one more question.
Sure.
What is the relationship between the regularity term that you had and the, epsilon optimality? Why, for example, does that term correspond to solving it within the particular error?
No, the point.
What is the relationship between these? I see heuristically that you should add a term of that sort. But can you justify it?
Yeah, of course. Like this term, what it does, it makes your problem strongly convex. That's the most important thing. So if I can add a term to make the problem strongly convex, I'm not thinking of a regularization for making, like, I don't assume any prior information about distribution, and this is like a prior model that you had. I'm just saying that the problem is convex. If I add a regularization that is order Vn, I'm not pushing the solution more than Vn. And already the solution, the accuracy that I want is order Vn, or 1 over the square root of n. So by adding a term that is order 1 over the square root of n, I'm not changing the complexity of the problem. Is that right? Okay, so where I was. Okay, so then the question is, so we want to make sure that n and m are related to each other in a way that the solution that you already have for this current problem is in the quadratic convergence neighborhood of the next problem, right? So then the question is, how should I use alpha? Alpha is the factor that I'm increasing the size of training set, right? So then in our work that was published in NIPS 2016, we showed that if alpha and c, where c is a factor in the regularization, if they both satisfy these two conditions, then everything that I said in the previous slide is going to work, and a single iteration of Newton's method is going to be enough. I mean, this is a nasty equation, but it has a nice interpretation. The first one ensures that the current iterate that you have is in the quadratic neighborhood of the quadratic convergence neighborhood of the next problem for the Newton's method. And this one ensures that once you update the iterate, the solution is going to be within the statistical accuracy of the next problem. So what's nice is, if the number of samples is large enough, this term is going to be always smaller than this one, and this condition is always satisfied. And you can also use large enough sample size to simplify the first equation, and you get this inequality. So if alpha and c satisfies this inequality, then you're done, and everything works. So simply, if I set alpha to be 2, which means that I double the size of training set at each iteration, if c satisfies this inequality where m is the Lipschitz continuity of gradient, then with single iteration of Newton's method, I'm going to solve each sub-problems. That means that basically, since I'm doubling the size of training set, with 2 passes over data, I'm going to reach a statistical accuracy of the full training set, right? And this means that since I'm doing this, since I increase the size of training set exponentially, the number of times that actually I have to compute the Hessian or inverse of that is going to be order log n, right? So now let's take a look at the performance of this algorithm for some real data sets. So here we have a logistic regression problem with 32,000 samples in this one and 5 million samples in this one. We see the performance of Adam Newton, Newton's method, and a first-order linearly convergent algorithm, a variance-reduced algorithm, SAGA. As you can see in both of these two plots, Adam Newton is faster than the other ones in terms of number of passes over data. But what is more interesting, I ran these algorithms over the test set, and look at the accuracy in the training set that if you reach that, you get the best test error. And that accuracy, which is also the statistical accuracy, is almost 10 to the minus 4, this dashed line that you can see here. And what's nice about Adam Newton, that it actually reaches this point after almost 2 passes over data, which matches our theoretical observation. Okay? So you might ask, okay, still you're computing the Hessian and Hessian inverse log n times. I don't want to do that. What if the size of training set, dimension of problem is very large? That's fine. You can also apply this to first-order methods or any iterative methods that you wish. For example, if the complexity of finding a point within the statistical accuracy of the full training set for accelerated gradient method is this, by applying this adaptive sample size idea on top of that, you gain a log n factor, both for deterministic method and the stochastic methods, right? So it's not as significant as what we observe for Newton's method, but we still obtain a log n factor. And in practice, we see that both for training error and test error, you obtain this log n factor, which is 4 here in this example, right? Okay. So far I talked about convex optimization, but now let's take a look at non-convex empirical risk minimization problem. So one of the main challenges in non-convex optimization is that first-order optimality condition does not mean global optimality. As you have saddle points in the problem. These are just 3 examples of saddle points where you have a point that the gradient is 0, but in one direction the function value is increasing, in another direction the function value is decreasing, right? So the challenge is, in most machine learning problems, is to escape from saddle points in order to make sure that you can at least reach a local minimizers. So if all the saddle points of the problem are escapable, then there is a hope to at least find the local mean for the problem. And in some instances of machine learning problems, you face a problem that reaching a local minimum implies finding global optimality. For example, in phrase retrieval or dictionary learning, if you escape from all the saddle points and find the local mean, you have actually found a global minimizer of the problem. Okay, so if we agree that escaping from saddle point is a challenging task, this is the goal, that first to come up with algorithms to escape from saddle points. And there are basically several different papers on ideas for escaping from saddle points, and this problem has been widely studied in the community of machine learning. But I can say that all these algorithms can be divided into 2 major groups. The first one is perturb the iterates by properly chosen noise. And the second idea is use second-order information to escape from saddle. So the first idea is saying that once I'm close to a saddle point, let's perturb it properly so that I can find the escape direction with high probability. And the second idea is, okay, look at the Hessian of the objective function and find the eigenvector corresponding to the smallest eigenvalue. That will give you escape direction. Okay, so that's nice. Both of these algorithms work. However, the computation complexity scales poorly with the size of training set. And if you have a large number of samples, the step of performing escaping from saddle point is going to be costly. So what we propose, we try to use the idea of adaptive sample size method also for non-convex problem. So saying that, okay, if escaping from saddle points is expensive, let's do it only once. So for the first problem, which has a small number of samples, let's say you escape from all the saddle points and you reach a local minimizer. And then you increase the size of training set, and you properly follow some iterative methods such that you trace a sequence of local minimizers, and you never get attracted to saddle points of the next problem that you face once you increase the size of training set. What's the advantage? You just escape from saddle points once, and for the problem with a small number of samples. What's the challenge? You want to make sure that once I increase the size of training set, and I follow some iterative updates, I don't get attracted to the saddle points of the next problem. Let me just explain the idea with a simple cartoon. So here, I start with a problem that has 1,000 samples, and I reach a point, I escape from all the saddle points, and I reach a point that is close to a local minimizer of the problem. If you can show that by increasing the size of training set, the local minimizer of these 2 problems are close to each other, then I'm already close to a local min of the next problem, and by performing some easy updates like gradient or accelerated gradient method or Newton's method, I can reach an approximate approximation of the local minimizer for the next problem. Then I can keep increasing the size of training set until I reach an approximate local mean for the problem with all the elements in the training set. Since the number of samples is large, a local mean for this problem is also close to a local mean for the expected risk minimization. And since I have a point close to that, I also have a point close to a local minimizer of expected risk minimization, right? So, but the question is, how can I ensure these 2 local minimizers are close to each other? What if I increase the size of training set and this local mean is close to a saddle point of the next problem? Right, that's a challenge. And in this beautiful paper by May and Montanari and the other collaborators, they show that if the function is a strongly Morse, then you can show that the critical point of the next problem, that is the closest one to this current local minimizer, is also going to be a local minimizer. And what is a strongly Morse? A strongly Morse basically saying that if you're close to basically saying that all the critical points are non-degenerate, which means that if you're close to a stationary point and norm of gradient is small, all the eigenvalues of Hessians are either larger than beta or smaller than minus beta, strictly away from 0, basically. So if this condition is satisfied, we can basically follow the idea of adaptive sample size that I explained. So basically, you find the local mean for the first problem, then you double the size of training set, and you find a point that has a gradient smaller than epsilon n. Once you have reached the score, then you go back to step 2 and double the size of training set until you reach the full training set, right? What's challenging, how can I ensure that I'm not get attracted to saddles? Well, if you properly choose this epsilon n, which is also 1 over square root of n, and you properly choose the initial size of training set, then you can ensure that the iterates never get attracted to other saddle points of the next problem. We formalize this result in this theorem. And we showed that if the number of samples, initial sample set, is large enough, which depends on the parameters of a strongly Morse definition, if you follow the update of accelerated gradient method, then after this many gradient evaluations, you're going to reach a point that has a small gradient value, which is exactly a statistical accuracy, and the Hessian at this point is positive definite. That means that this point, WN, that we have reached, is actually an approximate local minimum, because the Hessian is positive and the norm of gradient positive definite and the norm of gradient is small. Okay, and also if you use Newton's method, you can even improve the complexity or in terms of number of gradient evaluations to 2n, following the logic that I used for the convex case. And the number of Hessian computations is also going to be order log n, right? So, but here the complexity that I'm explaining is the cost to go from the local minimizer of the first problem to the local minimizer of the last problem. You want to see how much is the overall computation complexity and compare it with the state-of-the-art algorithms for finding a local minimizer of a strongly Morse function. So here I'm going to use accelerated Nesterov method, which was proposed by Carmond and his collaborators at Stanford for finding a local minimizer of a strongly Morse function. And using their algorithm, the complexity is going to be order n times sigma to the power of -7/2, where sigma is a parameter defined by a strongly Morse definition. And if you use this idea to find basically a local mean for the first problem, and then you follow the update of accelerated gradient method, you can improve the complexity to this, which is sigma to the power of -1/2. And if you just Newton's method in between of this, while you are increasing the size of training set, then the complexity is going to be order n. And this initial term that we have is, of course, the cost of finding the local minimizer for the first problem, which is significantly smaller than this, as m0 is significantly smaller than n. Okay? So basically, in this talk, I look at the problem of large-scale learning. And I started by talking about incremental or stochastic methods, and in particular, stochastic Quasi-Newton algorithms for solving large-scale learning. In the second half of the talk, I tried to use tools from a statistical learning theory to come up with more efficient algorithms for solving these large-scale learning problems that we face in machine learning and data science. But I'm just going to briefly talk about other works that I have done in different corners of this square. And I don't have time to go over the details, but I'll be more than happy to talk about the details of these projects. So in non-convexity, basically I look at the problem of escaping from saddle points. As I described, a challenging problem in most machine learning problems is to escape from saddle points to reach a local mean, which is sometimes a global minimizer. I look at this problem for both unconstrained and constrained problems, and we also applied this to navigation problems that appears in robotics. Another instance of non-convexity is submodular maximization. I mean, submodular maximization by nature is a discrete problem, and but some applications of submodular maximization in discrete domain is hard to solve in a computationally efficient manner. For example, if you want to solve a stochastic submodular maximization or decentralized submodular maximization, there is no efficient way to solve this in the discrete domain. So you would relax the problem and go to the continuous domain and solve the problem in the continuous domain using the tools that we know from continuous optimization, and then you use proper rounding scheme to go back to a discrete solution. What's nice about this idea is that the relaxed version of this problem, which is a continuous submodular maximization problem, is a special case of non-convex problem with a structure, which allows you to come up with a constant approximation guarantee for this problem. And we use this trick to solve a stochastic submodular maximization as well as decentralized submodular maximization, which lies at the intersection of non-convexity and distributed systems. So in distributed system, basically, we look at the problem that you want to minimize an objective function that is defined over a sum of a group of, basically you have a group of agents that each of them has access to a local function, and you want to come up with the minimizer of the global objective function without any global coordination. And this problem has been widely studied in the control community, signal processing community, and my work was basically on distributed approximation of Newton's method in both primal and dual domains, which lead to better algorithms in terms of overall communication cost. So another instance of distributed optimization that I look at is at the intersection of distributed systems and large-scale learning. Imagine that you have a massive number of samples, and you distribute these samples over several machines. But since the number of samples that you assign to each machine is beyond its computational capacity, each of them has to use only a subset of samples to update the model. right? In such setting, you are in the regime of stochastic decentralized methods, and in this paper, we came up with the first linearly convergent algorithm for this setup, and in the follow-up paper that we published in ICML, we improved the complexity bounds in terms of condition number of graph and condition number of problem. And last but not least, I also look at the problem of time-varying optimization and trying to formulate this problem as a dynamic online learning problem and looking at the regret bounds that we can get for first-order methods. And for a specific applications domain, when you can assume some sort of assumption about the variation of the functions over time, we could come up with a prediction correction idea where you use basically the variation of functions that you have seen so far to predict what's going to be the behavior of the function after this iteration. And using this prediction correction methods, we could come up with better error bounds for time-varying optimization problems. Okay, so far I talked about the works that I have done, but let me just briefly mention some of the future research directions that I aim to explore in the next few years. So basically in large-scale learning, I'm looking at two different problems. One of them is memory-efficient algorithms. So the algorithms that we have developed so far, they're computationally fast, and they can achieve the rates that we aim for, that we like to achieve. But however, they sometimes require a memory that scales with the size of training set. The question is, can we come up with memory-efficient algorithms that also achieve the rates that we aim for? The second problem that I'm very excited to work on is on continuous limit interpretation of iterative methods. So most iterative methods can be interpreted as a discretization of an ODE. And using this perspective, you can come up with algorithms that are better for solving large-scale learning or coming up with new tools for analyzing iterative methods, which is something that we did in our recent work that was published in NIPS for understanding acceleration using continuous limit interpretation of Nestrov's method. In the domain of non-convex optimization, my work has been mostly on the idea of coming up with more efficient algorithms. But I'm also interested to looking at the ideas for improving the landscape of non-convex optimization. For example, you can use regularization idea or lifting idea so that you don't change the local mean or global mean of the problem, but using these two, for example, regularization idea, you can get rid of the bad saddle points that the problem might have. This is another interesting direction I'm excited to work on. And the last thing in non-convexity is I'm interested about the interplay between learning and optimization. For example, what kind of formulations lead to what sort of formulation, if we come up with, the solution is going to have a better generalization error? Or for a specific formulation, what sort of algorithm, if I use, the solution is going to have a better generalization bound? So these sort of problems, which lies at the intersection of learning and optimization, is also very interesting and I'm excited to work on. In the area of distributed optimization, I have worked so far on designing fast algorithms for solving this class of problems. But I think it's the right time to bring tools from information theory to make these algorithms communication efficient, private, and robust against adversarial attacks and stragglers. So far we just look at the first problem, which is using the idea of quantization to come up with communication efficient algorithms. But indeed, there are different ideas in information theory that you can come up with private and robust algorithms. And in the last corner, which is time-varying optimization, I'm excited. So far, I have looked at problems where the cost function of the problem is changing over time. But motivated by many applications, including power systems, we are also excited to look at the problems that the constraints of the problem changes over time. And this is another interesting topic that has application in power systems. And also, I'm interested to look at applications of the time-varying optimization and distributed systems in Internet of Things and autonomous systems. So in both of these application domains, you face a physical system in which a group of agents are gathering information, talking to each other, and without global coordination, they want to come up with an optimal decision in an environment that might change over time. So we basically need tools from time-varying optimization and distributed optimization to understand, to come up with basically optimal decision-making protocol for these two application domains. Okay, so before closing my talk, let me thank my amazing collaborators that without their help, I couldn't do any of these projects. And let me thank you again for attending this talk, and I would be more than happy to answer your questions. Thank you.